Today, the topic of discussion is on basic concept of strength of material, that is Module 1, Part 7, PCME 403. Myself, Dr. Suman Das, HOD, Department of Mechanical Engineering, Swami Vivekananda Institute of Science and Technology. So in this video, I will discuss principal stresses and principal planes and Mohr cycle. Now, what is biaxial stress? So let us now consider the stress element ABCD, where tau xy equals to 0, sigma x and sigma y is there. This type of stresses is known as biaxial stress. That means there is no tau xy, only sigma x and sigma y are present. In the previous equation, if we put tau xy equals to 0, we will get the normal stresses and sigma n and shear stresses. So the tau on the plane at angle theta, so the normal stresses should be sigma n is nothing but sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta. Similarly, the shear stresses or tangential stress, that is tau, is nothing but sigma x minus sigma y by 2 sine 2 theta. Now here the aspect angle is theta, so this is the theta aspect angle. That means this is the plane cut by the element with an angle theta. So ABCD is a square element or rectangular element, whatever may be, and that theta varies from 0 to pi by 2. So this is the theta varying from 0 to pi by 2. Now this is sigma x, this is sigma x, and this is sigma y and sigma y. So there is no tau xy. So the normal stress sigma n varies between the values, that is sigma x, that is theta equals to 0, to sigma y theta equals to pi by 2. That means the angle theta, that is 0 to pi by 2. Similarly, for the complementary stresses, the aspect angle should be, already I have discussed in my previous video. So we have to add 90 degree with the angle theta. So we will get the complementary shear stresses aspect angle. Now let us take an example. The principal tensile stresses at a point across two perpendicular planes are 100 MPa and 50 MPa. So find the normal and tangential stresses and the resultant stresses and its obliquity on the plane at 20 degree with the measured principal stresses. So we just put the given value, that is sigma x is known here, 100 MPa, that is positive. Sigma y is also 50 MPa, that is also positive, that means tensile. And the aspect angle, that is theta equals to 20 degree. Now from the equation of sigma n, so we just put the value of sigma x and sigma y and the value of angle theta. So directly we will get the value of sigma n, that is the 94 MPa. Similarly, the shear stress tau will just sigma formula with the help of the formula sigma x minus sigma y by 2 sine 2 theta. So just putting the value of sigma x and sigma y and the value of theta, we are getting, that is tau equals to 16 MPa. Now the resultant sigma r, that is nothing but the root over of, that is the sigma n square plus the tau square. That's, so we are getting 5.4 MPa. Therefore, the angle of obliquity is very simple, that is tan inverse tau by sigma n. So we just put the value and we are getting the angle of obliquity, that is the value of theta. Now ABCD is the element, so we just put all the values, that is sigma x and sigma y, and this norm sigma n, that is sigma resultant r, that is this is tau, and this is the aspect angle 20 degree. Okay, and this is the phi, that is 9.7. So all the values are shown in this element ABCD element. Now we may derive the uniaxial stresses on oblique planes. So this is the formula, that is the value of sigma n, and this is the value of tau in this of oblique plane. Oblique plane means this is the angle. This one is the oblique plane. Here So sigma y equals to 0 and tau xy equals to 0. Therefore, we just getting the sigma in, just putting this value of sigma y should be 0 and tau xy equals to 0. So this is the value of sigma n. Similarly, the tau should be like this. Now the pure shear. Pure shear is particular case of biaxial stresses where sigma x equals nothing but minus sigma y. That is the pure shear. So sigma x or sigma y, which is compressive, that is immaterial, but one should be tensile and other should be compressive. So if sigma x is tensile, in that case the sigma y, that means the others normal stresses should be the opposite, that means the compressive. So if sigma x equals to 100 MPa, then sigma y must be minus 100 MPa. So, and otherwise, if sigma y equals to 100 MPa, in that case, in this sigma x should be minus 100 MPa. Okay. So in the case of pure shear on 45°, we just put the, so tau max is nothing but plus minus sigma x. So here the sigma n equals to 0, normal stress, that is 0, and sigma n, that is sigma n dash, that is the complementary normal stress, that is also should be 0. Now we may deposit the pure shear in an element by following two ways. So this is the element, and this is the ABCD is the rectangular or square element, and this is the tau xy, this is tau xy, this is tau xy, and in the torsional member, so this member is subjected to torsion, that is torque, the twist. An element ABCD in a pure shear, only shear stress in the present in this element. So only if you see that only the shear stresses is there, tau xy here, tau xy here, tau xy. Okay, there is no direct stress. In the element that is 45° plane, an element that is A dash, B dash, C dash, D dash. So this is the A dash, this is B dash, this C dash. Just you rotate this ABCD element in a 45° angle as per the statement. In pure shear, where sigma x equals to minus sigma y, but in this element no shear stresses is there. So only, so if you just rotate this element, so sigma should be minus tau, and here sigma is the tau. Okay. In a biaxial stage, that means ABCD, the biaxial stage that means the sigma x and sigma y both are present. In the biaxial state of stress, a member as shown below, an element ABCD, ABCD is an element in a pure shear where sigma x equals to minus sigma y, sigma x equals to minus sigma y, minus sigma is equals to minus sigma y, but the element no shear stresses is there, and an element A dash, B dash, C dash, D dash. So this is A dash, B dash, C dash, D dash at 45° angle. We just rotate this element in the 45° angle plane is also input shear, only shear stresses in present in this element. So that is, if we just rotate this element, so only the shear stresses will be there. So there is no normal stresses. Now, principal stresses and principal plane. When examining stress at a point, it is possible to choose three mutually perpendicular planes on each. No shear stresses exist in three dimensions. One combination of orientation of the three mutually perpendicular planes will cause the shear stresses on all three planes to go to 0. This is the state defined by the principal stress. So principal stress are normal stresses that are orthogonal to each other. That means the stresses that are perpendicular to each other, that stresses are called the principal stress. So here, if you see the diagram, so the principal planes are now the principal planes are the planes across which principal stresses act. So this is the principal stress, and this is the principal plane. That means principal stresses perpendicular to the principal plane. So that's why it is written principal planes are the planes across which principal stresses act faces on the cube. So this is the faces on the cube. So these are the principal planes. Principal stresses, shear stresses are, that means on the principal stress. On for so for principal stresses, shear stresses are zero. So on the principal plane, there is no shear stress. So this is the formula of major principal stress, and this is the formula of minor principal stress. So sigma 1 is nothing but sigma x plus sigma y by 2 root over of sigma x minus sigma y by 2 whole square plus tau xy whole square. So we can write in this way: sigma 1 comma sigma 1 comma 2 is nothing but sigma x plus sigma y by 2 plus minus root over of sigma x minus sigma y by 2 whole square plus tau xy square. So one should be positive, that is the major principal stress. One should be negative, that is the minor principal stress. Similarly, position of principal planes, so that is the angle. So this is the formula 2 tau xy by sigma x minus sigma y. Similarly, tau max should be sigma 1 minus sigma y by 2. So that is nothing but root over of sigma x minus sigma y by 2 whole square plus tau xy whole square. Now, with an example, in the wall of the cylinder, the state of stress is given by tau xy is, that is given, that is negative 85 MPa, and tau and sorry sigma x equals to 85 MPa, that is compressive, sigma y equals 25 MPa, that is tensile, and tau xy equals to 60 MPa. So what we have to calculate? We have to calculate the principal planes on which they act. So principal planes on which they act, and so this is the given value: sigma x is 85, sigma y equals to 0, and sigma xy equals to 0. So with the help of the direct formula, so major principal stresses sigma, that means sigma 1, we just, with the help of this formula, we just put the value and getting the value of sigma 1. Similarly, for the major minor principal stresses, so sigma 2 is nothing but, here the it is positive and here should be, this should be negative. So all the values are same: sigma x minus plus sigma y by 2 minus root over of this, and we just put the value of sigma x and sigma y, and we are getting the value of the sigma 2, that is the compressive in nature. So sigma 1 equals to major principal stress, that is positive, and sigma 2, that is the minor principal stress, that is negative. For principal planes, same way, so we can easily calculate the value of principal planes, that is the theta angle. So theta equals to minus 24. So complementary, all of already have discussed the complementary means the we have to add the 90-degree with this angle. So we are getting 66-degree. It is for sigma 2. So in this figure, it is clear that the value of sigma x and this is sigma y. So sigma x equals to compressive, that is negative. Sigma y is positive, tensile, and this is um, the reference angle BC, reference plane BC. So if we just rotate this one, so this is the theta equals to 24. So we are getting the value of sigma 1 and sigma 2. Now it is very important, the direction of one principal planes and the principal stresses acting on this would be sigma 1 when is acting normal to the plane. Now the direction of the other principal plane, that is theta plus 90, theta plus 90 plus theta, because the principal planes are two mutually perpendicular planes. Hence, rotate the another plane 90 plus theta p in the same direction to get the another plane. Now complete the material element theta p is negative, that means we are measuring the angles in the opposite direction to the reference plane. The following are the figures gives the clear idea about the negative and positive theta. So if you see the diagram, so this is the direction of the principal plane and this is the reference plane, and on the reference plane the left side should be positive and the right side should be negative, and that angle should be minus p. Okay, so that is stated here. Now the Mohr cycle for plane stress. The transformation equation of the plane stress can be represented in graphical form, which is popularly known as Mohr cycle. So, though the transformation equation are sufficient to get the normal and shear stresses on any plane at a point, with Mohr cycle one can easily visualize their variation with respect to the plane. That means Mohr cycle is nothing but the graphical representation of the state. So we will now discuss this Mohr cycle with the help of graphical representation in the next video. Now this is the nothing but the equation of Mohr cycle. So the sigma n, that is the value already I have mentioned in my uh, in this video. So that is the tau, that is nothing but sigma x minus sigma y by 2 sine 2 theta, tau minus tau xy cos 2 theta. And so if we rearrange this, we will get this. Similarly, tau equals to this. Now, a little consideration will show that the above two equations are the equation of the circle, and sigma n and tau y are the coordinates. Coordinate theta 2 theta is the parameter. So here, when we represent the sigma and tau, so one sigma is this, so sigma and tau, there should be two axes, and just you have to theta is the and its coordinate, and 2 theta is the parameter. So this is the average sigma, that is sigma x plus sigma y by 2, and this is the resultant of that. So um, sigma n minus sigma average whole square plus tau xi is nothing but the r square, the resultant. Now it is the equation of a circle, so that is sigma average 0, and average is nothing but that is the sigma x plus sigma y by 2 comma 0, and resultant r is nothing but root over of this. Okay, thank you very much.